We covered a lot of ground in this course, so in this last unit, let's look at what we've studied, at least some of the things that we studied, and see how they relate to some of the things that you will be spending a lot of your time in the computer science program doing. So one question that I often get by this time in the course, we've done so many different things, but what do they have to do with programming? If I'm going to become a programmer, how is it going to be useful? And hopefully in this short kind of putting it all together lecture, I will try to say a little bit of how some of the things that you've seen in this course may come handy. So first of all, designing algorithm programming requires precision, requires understanding what it is exactly that you need to solve. And for that you need a language. And now you have it. That's the language of logic. And as we will see in a couple of slides, a lot of time when you're trying to explain what your program is supposed to be doing, using logic is very, very useful because it lets you say things like everything exists for all as opposed to any. It lets you formulate exactly what specification your program should follow in order to be correct. And once you have specification, again for which you would be using the language of logic, you will need to show that whatever code you wrote indeed works correctly. You will see it later in some other courses, but a way to show that something works correctly is proofs. And that's proofs very much in the style that we've done. In particular, induction and strong induction are very common tools in showing that your program runs correctly. Another thing that you will see a lot of is different, they call discrete structures, such as sets, relations, graphs, and so on. We've seen a ton of those. Probably the main thing that you're going to see is how they're used to model problems. So you could start with a problem that talks about, say, a traffic network or a Facebook, friends, and you would convert it into a graph so that you could apply algorithms that you will learn in 2002 that are generic algorithms that run on graphs and that can solve those problems much faster than you would if you didn't code them as graphs. So knowing what those structures are, being able to code them as is a prerequisite to being able to code them as data structures, which will in turn let you both solve the problems and do it efficiently. So now that we started talking about efficiency, well, we discuss in this course several concepts that are crucial to talking about what it means for a program to have good performance. So in particular, we looked at recurrent relations, and we talked about how to give a guarantee on how long the program will take. For example, we showed how many steps the Tower of Hanoi problem needs. So any algorithm that solves the Tower of Hanoi problem needs that many steps, and you could do it in this time. And we talked about big O notation that you will see in pretty much every algorithm and many other courses. Well, pretty much any course that mentions algorithm, and most of computer science courses do, because we tend to talk about performance, ignoring the constant, ignoring lower order terms, and big O notation is how we talk about what the complexity of specific algorithm, and in general we use those concepts to talk about complexity of computational problems. And a lot of time when you're trying to determine how long the program needs to run, it boils down to how many possible options it has. And this is where combinatoric comes in, because now you know how to calculate different options of many different kinds. Well, performance in worst case is a good concept because it gives you guarantees that your program is not going to run slower than whatever your guarantee is. But a lot of time you would be interested in average performance, because maybe there are some really complicated cases, but on average your program will work well. And for that, you will need the language of probabilities, expectations. Expectation comes in a lot there. And you will use it to estimate how long program may take on average. Usually, estimating how long something takes on average is not a very easy task because you will need to make assumptions about probabilities of different inputs. But at least when you do have those assumptions, the language of probabilities, expectation, Bernoulli trials will let you talk about performance of a program on average. So let's look at a very simple example. Suppose you have an array, let's say a whole bunch of boxes, and you want to find a specific element, x, in this array. So you will be asking, so which box contains, in this case, the blue candy? Say, okay, so this is a box number 4. Okay, I will return the number 4. So where would you use logic? This seems like a very kind of English is enough kind of thing. Well, if you just took the description that I showed you and tried to implement it, you would realize that there are several important details missing. You know this quote, the good news about computers is that they do what you tell them to do. The bad news is they do what you tell them to do, which may not necessarily be what you want them to do. That's a completely different thing. So you need to be precise about what you want them to do in order to be able to tell it to them. How do we do it here? So we will use the terminology, and you'll see it in your later courses, of precondition and postcondition. Precondition is just a logic statement that says, before you start the program, the following must be true. And if this thing is not true, well, then your program is not obliged to do anything reasonable, really. Postcondition is what should be true after a program finished, provided that the precondition was satisfied. So for example, in the searching for a candy in the array, if, for example, you might want to say, oh yeah, the array is not empty. Or you might want to say that x is a number or a candy. Or you might want to say that x must be in the array. I know it's there, I just don't know where. And depending on those assumptions, the guarantees on what you will output would be different. For example, you may say, well, return the value of a box which contains the candy. Well, you need to also say, you need to either put in the precondition that the candy is somewhere in this row of boxes, or you have to say what to return when that x is not in the array. So now you see how if you formulate it in more, again, we are still not using logic notation, but if you can formulate it more formally, then you start noticing those little things. Also, so here I'm saying if the program returned a value k, then a of k equals x. What if the program did not return a value k? Well, in this case, all bets are off, so maybe that's not a good way to formulate it. Maybe I want to say the program will return the value k such that a of k equals x. And if x is not in the array, it will return, for example, -1, something. Also, as you are writing the program, this course does not require computer science prerequisites, so I'm kind of hesitant to show you much of code, even pseudocode. But think about how you would implement it. Could very well be that your first operation would be, let's look at the first box and see if x is there. Well, what if your array is empty? What if you don't have any boxes? Then your first operation, let's look at the first box, is going to fail. There is none. Again, this is something that you will want to explicitly state in a precondition for the program, explicitly state in specification to avoid those pitfalls. And logic is something that's very useful for doing things like that. Okay, so just to give a very, very brief summary, to prove correctness of algorithm, correctness of program, first you need to show that if you start with precondition being true, then after running the program, you end up with a postcondition being true. If the array is not empty and X is somewhere in the array, then after the program stopped, it returns a number which is the index of a cell in the array which contains X. Precondition and postcondition apply not only to the whole programs, but even to little pieces of them. You could say this part of the program has this precondition and this postcondition. Sometimes, though, you have something more complicated in the program, such as a loop. When we have a loop, we could still prove its correctness, and the proof is actually by induction. That's the very induction that we've studied in this class. We say, well, before the loop started, something is true, that's our base case. If the previous iteration of the loop was correct, then the next iteration of the loop is correct. And then we need to separately say, and by the way, the loop stops sometimes, and so whenever it stops, what was correct after every iteration is still correct, so the loop works fine. Sometimes it's even more complicated than loop. Sometimes the program may be recursive, may be calling itself, or maybe calling other programs. In this case, you would use strong induction in order to prove its correctness, because then you could prove things like if the program doesn't make any recursive calls, and well, it should, otherwise it will run forever, then it's correct, base case. And for induction hypothesis, let's assume that all recursive calls return a correct answer, then the program itself returns a correct answer. Again, this is a very proof by induction, by strong induction that you've seen in this course. So let's now talk about the running time. Suppose our program worked correct, and now the question is, how long does it take to run? So suppose our precondition doesn't really matter here, that A is an array that contains X. X can be anywhere between the first box, let's say box number 0, and the last box, box number n-1. So in the worst scenario, the algorithm that we have will have to look at every single box. There are n of them, so running time is big O of n. And actually, this was a pretty simple example because there was nothing recursive. We didn't even need recurrences. So now you may say, wait a moment, but this is the worst possible case. This is if the candy is in the very, very last box. You look everywhere and only the very last place you look contain what you were looking for. But it's only the worst case. The worst case doesn't happen, hopefully, every day. So on average, how much you would expect, how many cells you expect to check before you find X? Well, this depends on the probability of X being in each cell, because if you know that half of your boxes contain blue candies, that's one scenario. Or then it's very easy to find a blue candy on average. But if there is only one, then you expect to spend a lot more time. So here is where you could refer to the Bernoulli trials and how to check the expected time until you get some result. So suppose for every cell of the array it contains X with probability P. Then, by the formula that we studied in the last unit, the expected number of steps before we find X is 1 over P. So for example, if every box contains what we want with probability 1/2, so like on average half of the boxes contain blue candy, then on average we'll expect to see a blue candy in 2 steps. On the other hand, if probability of the candy being in every box is 1 over n, that is, there is one candy that we are looking for and it can be in any one of the boxes with equal probability, well, then you expect to spend a lot more time n to find it. On average, you could show that this will be roughly n over 2 time to find something in an array of size n, which by the way is still big O of n. So the complexity of this algorithm on average is roughly the same as complexity in the worst case, unless you're looking for something that occurs with very, very high constant probability. Okay, so that's it for the course, and you will see a lot of this in other courses. You will see references to all sorts of things, and hopefully you will remember the keywords that you could use to Google for it. Thank you for being part of the journey, and have fun.